Oke, baik. Selamat malam semuanya. Hari ini kita minggu yang ke-10. Kita akan belajar mengenai Math for Machine Learning untuk yang PCA. Oke, layar saya sudah terlihat. Baik, sudah ya. Oke. Sudah minggu ke-10 aja ya ini matematika hari ini, pelajaran yang terakhir tentang matematika di pelatihan ini. Jadi kemarin kita udah belajar tentang linear algebra, lalu multivariate calculus, dan yang sekarang kita belajar tentang PCA, Principal Component Analysis. Oke, agenda hari ini kita akan membahas mengenai statistic of dataset dan inner product. Oke, apakah semuanya sudah siap? Pasti siap dong ya. Gimana nih? Udah di minggu-minggu hampir terakhir nih. Jumat depan kita udah final exam. Oke, kita lanjut aja ya. Oke, sedikit recap. Kira-kira masih ingat nggak nih, kemarin minggu ke-9 kita belajar tentang apa? Ada yang masih ingat nggak? Boleh ditulisin di kolom chat. Gimana nih? Minggu ke-9. Tentang device-based model in TF Lite. Kita juga belajar data pipeline di minggu ke-9 ya, kemarin. Oke, kita next. Nah, pelajaran hari ini kita akan memahami PCA dari sudut pandang geometri. Lalu kita akan belajar cara summarize dataset dengan statistik dasar. Selain itu, kita juga akan mempelajari mengenai perubahan mean dan variance saat kita shift atau scale original dataset. Akan ada Jupyter Notebook yang membantu pemahaman matematika dengan coding. Jadi ini akan kita lakukan hari ini. Nah, sedikit pengenalan. PCA atau Principal Component Analysis itu merupakan salah satu algoritma dimensionality reduction terpenting dalam machine learning. Tapi kita masih belum membahas terlalu dalam mengenai PCA langsung. Jadi hari ini kita fokus ke dataset dan inner product dulu. Nanti hari Jumat kita akan bahas mengenai PCA. Oke, part yang pertama itu statistik. Oke, di sini ada calculating mean, variance, and standard deviation fairly explained. YouTube. Oke, sebentar aku share sound terlebih dahulu. Oke, share sound.
I was up last night thinking about the mean variance.
Oke, sebentar. Kok bahasanya Korea? Oke.
I was up last night thinking about the mean variance and standard deviation. So I estimated them, and it was cool. StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to continue our series on statistics fundamentals. This time we're going to talk about estimating the mean, variance, and standard deviation. Note, this StatQuest assumes you already know about histograms, statistical distributions, and, specifically, the normal distribution. If not, check out the quests. The links are in the description below. Also, this StatQuest assumes you already understand why we want to estimate population parameters. If not, check out the quest. In the StatQuest on population parameters, we counted the number of mRNA transcripts from gene X in 5 different liver cells. Alternatively, if mRNA transcripts in liver cells didn't mean anything to you, we counted the number of green apples in 5 different grocery stores. Or green t-shirts in 5 different clothing stores. Or whatever you want to measure in 5 different units. This green dot represented a liver cell that had 3 mRNA transcripts for gene X. And this green dot represented a liver cell that had 13 mRNA transcripts. 19, 24, and 29. Now, if we had a lot of time and money on our hands, we could count the number of mRNA transcripts for gene X in all 240 billion liver cells. Now we can draw a histogram of the measurements. If we wanted to fit a normal curve to this histogram like this, then we need to calculate the population mean and the population variance or population standard deviation. Calculating the population mean is easy. We take the average of all 240 billion measurements. And we get 20 for the population mean. And we center the normal curve on the population mean. Note, because we calculated the mean with all 240 billion measurements in the population, this is not an estimate of the population mean. It is the population mean. However, since we rarely, if ever, have enough time and money to measure every single thing in a population, we almost always estimate the population mean using a relatively small sample. In this example, we have the measurements from only 5 of the 240 billion cells. Estimating the population mean is super easy. We just calculate the average of the measurements we collected. And in this case, the estimated population mean is 17.6. Oh no, it's the dreaded terminology alert. Statisticians often use the symbol X bar to refer to the estimated mean, which is also called the sample mean. And they use the Greek symbol mu to refer to the population mean. The estimated mean, X bar, is different from the population mean, mu, but with more and more data, X bar should get closer and closer. Going back to the full set of population data, we will now determine how wide to make the curve by calculating, not estimating, the variance and standard deviation. In other words, we want to calculate how the data are spread around the population mean. This is the formula we use to calculate, not estimate, the population variance. Note, I'm making a big deal about calculating versus estimating variance because it makes a big difference that we'll talk about later. This part, x minus mu, means we subtract the population mean, mu, from each measurement, x. Boop 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 boop. Boop boop. The square tells us to square each term. And the Greek character sigma tells us to add up all the terms. Lastly, we want the average of the squared differences, so we divide by the number of measurements, n, which in this case is 240 billion. Thus, we're just calculating the average of the squared differences between the data and the population mean. Note, squaring each term ensures that each difference is positive.
Selama gap year ini, aku banyak menggunakan Grammarly untuk
Otherwise, the measurements on the left side of the mean would give negative differences, which would cancel out the positive differences from the measurements on the right side of the mean. Note, if you are wondering why we don't take the absolute value of each term, great! We'll talk about that in the follow-up video that dives deep into these details. Anyway, now we just do the math. And we get 100 for the population variance. Bam! Okay, we calculated the population variance and we're all proud of ourselves. However, there is one thing that is annoying about it. Because each term is squared, the units for the result, 100, are mRNA transcripts squared. Note, if the data had been the number of apples in grocery stores, then the variance would be 100 apples squared. Either way, we can't plot the variance on the graph since the units on the x-axis are not squared. To solve this problem, we can take the square root of everything, and that gives us the population standard deviation. So the population standard deviation is the square root of 100, the population variance, which is 10. And we can plot that on the graph. This shows the mean, 20, plus and minus the standard deviation, 10 mRNA transcripts. Bam! Note, before we move on, I want to emphasize the point that we almost never have the population data, so we almost never calculate the population mean and population variance and standard deviation. Instead, we estimate the population variance and population standard deviation from the relatively small number of measurements that we have. Remember, the population variance and standard deviation determines how much the curve spreads out. And that means the estimated variance and the estimated standard deviation should reflect how the data are spread around the population mean. However, when we do an experiment, we don't see the curve or the population mean. We only see the data. So we have to use the estimated mean, x bar, instead. This is the formula we use to estimate the population variance. Because we almost always work with a relatively small sample and not the entire population, this is the formula we will use most of the time. The differences between this formula and the one for the calculated population variance are subtle but important. First, since we don't know the population mean, mu, we use the sample mean, x bar. Second, we are dividing by n minus 1 instead of n. Dividing by n minus 1 compensates for the fact that we are calculating the differences from the sample mean instead of the population mean. Otherwise, we would consistently underestimate the variance around the population mean. This is because the differences between the data and the sample mean tend to be smaller than the differences between the data and the population mean. Thus, the differences around the population mean will result in a larger average. and the larger average is what we are trying to estimate. Note, if you're like me and want to know more details about why we need to compensate for calculating differences from the sample mean, check out the follow-up StatQuest. The link is in the description below. Now let's do the math. Just like before, we calculate the differences between the mean and the data. Then we square each term, but now we divide by n minus 1. And the estimated population variance is 101.8. Now we just take the square root of the estimated variance to get the estimated standard deviation. And we get 10.1. And we can draw the mean plus and minus the standard deviation on the graph. Double bam! The estimated population parameters correspond to this purple curve, with mean equals 17.6 and standard deviation equals 10.1. Which isn't too far off from the true distribution, with mean equals 20 and standard deviation equals 10. With more data, the estimated parameters would be more accurate and we would have more confidence in them. However, with just 5 measurements, we still did pretty well, and that saved us a ton of time and money. Hooray! In summary, if we have all of the data from a population, we can calculate the population mean. The population mean equals the sum of the measurements divided by the number of measurements, and that equals the average measurement, mu. When we don't have the population data, we can estimate the population mean with the same formula. The estimated population mean equals the sum of the measurements divided by the number of measurements, which equals the average measurement, x bar. When we have the population data, we can calculate the population variance and standard deviation. The population variance is the average of the squared differences between the data and the population mean, mu. In other words, we square these differences to prevent the ones on the left from canceling the ones on the right, and then take the average. And the population standard deviation is just the square root of the population variance. And since the standard deviation is in the original units that we measured, we can draw it on the graph. However, we almost never have the population data, so chances are you should not use these formulas. Instead, we almost always estimate the variance and standard deviation. When we estimate the population variance, we divide by n minus 1 to compensate for measuring distances from the sample mean instead of the population mean. And the estimated standard deviation is just the square root of the estimated population variance. And since the standard deviation is in the same units that we measured the data, we can draw it on the graph. And one last shameless plug for the follow-up StatQuest. If you want to know why dividing by n underestimates the variance, check out the quest. The link is in the description below. Triple bam! P.S. In this StatQuest, I made a big deal about how we rarely have the population data and we almost always estimate the population parameters. One reason I did this was because, while many software packages estimate the variance and standard deviation by default, Microsoft Excel does not. Instead, it gives 2 choices. One function, var.p, calculates the population variance. The other, var.s, estimates it. Since we almost always have a relatively small sample rather than the population data, we should almost always use var.s. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to
Oke, ini tadi dijelasin ya cara hitung mean. Terus juga tadi yang dari variance population. Oke, aku tadi kayaknya ada yang kelupaan sebelum ini. Oke, tadi di sini kan ditulis ya algoritma dimensionality reduction. Nah, ada yang tahu nggak nih data reduction tuh kayak apa? Dengan PCA itu data reduction. Ya, ada meningkat dimensi, pengurangan dimensi data. Oke. Kalau data reduction ya meringkas kayak Ania sama kayak pengurangan dimensi data. Jadi biasanya kalau di PCA itu datanya nggak harus berbentuk satu data juga, terus juga representasinya langsung semua data gitu nantinya. Jadi untuk kita pakai buat meringkas dimensinya gitu. Oke, itu ya. Oke. Jadi kita lihat yang varian, sekarang kita coba lihat yang covariant.
It's in the window. My cat can
Masih Korea.
My cat can't do stats in the window. So I'll do stats for her all day long. Stat Quest. Hello, I'm Josh Starmer and welcome to Stat Quest. Today we're going to talk about covariance, and this is part 1 in a 2-part series on covariance and correlation. Note, this Stat Quest assumes that you are already familiar with the concept of variance. If not, check out the quest. The link is in the description below. In the Stat Quest on variance, we started with the number of mRNA transcripts for gene X from 5 different cells. And if mRNA transcripts aren't your thing, you could think that we counted the number of green apples in 5 different grocery stores. Then we estimated the mean, X bar. And then we estimated the variance. Bam. And that's our review of variance. Imagine that in addition to counting mRNA transcripts for gene X, we also counted gene Y transcripts in the same 5 cells. Alternatively, you can imagine we counted the number of red apples in the same 5 grocery stores. Note, if you're wondering why gene Y is perpendicular to gene X, don't sweat it. The reason will become clear in just a bit. Anyway, just like we did for gene X, we can estimate the mean for gene Y. And since gene Y is on the y-axis, we will use y bar to represent its mean value. And we can estimate the variance. Bam! So far, we've estimated the mean and variance for 2 different genes measured in the same 5 cells. Alternatively, you could imagine we estimated the mean and variance for 2 different types of apples counted in the same 5 grocery stores. Since these measurements were taken from the same cells or the same grocery stores, we can look at them in pairs. For example, this pair of measurements came from the same cell, and both measurements are less than their respective mean values. This pair of measurements came from another cell, and both measurements are greater than their respective mean values. Since the measurements were taken in pairs, the question is, do the measurements, taken as pairs, tell us something that the individual measurements do not? Covariance is one way to try to answer this question. Since the measurements came from the same cells or grocery stores, we can plot each pair as a single dot by combining the values on the x and y axes. Now, generally speaking, we see that cells with relatively low values for gene X also have relatively low values for gene Y. And cells with relatively high values for gene X also have relatively high values for gene Y. This relationship, low measurements for both genes in some cells and high measurements for both genes in other cells, can be summarized with this line. Note, the line that represents this particular relationship has a positive slope, and it reflects the positive trend where the values for gene X and gene Y increase together. In other words, if you told me that there were a lot of transcripts for gene X in a cell, then the trend suggests that the same cell should have a large number of transcripts for gene Y. Likewise, if you told me that you had a low value for gene Y, then the trend suggests that the same cell should have a small number of transcripts for gene X. If the data had looked like this, and relatively low values for gene X corresponded with relatively high values for gene Y, and relatively high values for gene X corresponded with relatively low values for gene Y, then the relationship would have a negative slope and reflect the negative trend that the values for gene X increase as the values for gene Y decrease.
Selama gap year ini, aku banyak menggunakan Grammarly untuk menulis personal statement yang nanti akan aku gunakan untuk
If the data had looked like this, and every value for gene X was paired with the same value for gene Y, as the values for gene Y decrease. If the data had looked like this, and every value for gene X was paired with the same value for gene Y, then there would be no trend, positive or negative, between gene X and gene Y. This is because if you told me that you got the same measurement for gene Y found in all of the other cells, then we would not know if the same cell should have a relatively small value for gene X, or a relatively large value, or any other value. Likewise, if every value for gene Y was paired with the same value for gene X, there would be no relationship. This is because if you told me that you got the same measurement for gene X found in all of the other cells, then we would not know if the same cell should have a relatively small value for gene Y, or a relatively large value, or any other value. The main idea behind covariance is that it can classify three types of relationships. 1. Relationships with positive trends. 2. Relationships with negative trends. And 3. Times when there is no relationship because there is no trend. Okay, we just covered the main idea behind covariance. It's so important that I'm going to repeat it. Covariance can classify these three types of relationships. 1. Relationships with positive trends. 2. Relationships with negative trends. And 3. Times when there is no relationship because there is no trend. Bam! The other main idea behind covariance is kind of a bummer. Covariance, in and of itself, is not very interesting. What I mean by this is that you will never calculate covariance and be done for the day. Instead, covariance is a computational stepping stone to something that is interesting, like correlation. Because I like repeating myself, let me repeat the second main idea behind covariance. Covariance is a computational stepping stone to something that is interesting, like correlation. So let's talk about how covariance is calculated. Covariance is calculated with this slightly nasty looking thing. To get an intuitive sense for how covariance is calculated, let's go back to the mean value for gene X and extend the green line to the top of the graph. And then extend the red line that represents the mean for gene Y to the edge of the graph. Now let's focus on the leftmost data point. Since it's to the left of the solid green line, we see that it is less than the mean value for gene X. And since it is below the solid red line, we see that it is less than the mean value for gene Y. Now let's plug in the gene X measurement for this cell and the mean value for gene X. And that gives us this difference.
Bringing your ideas and innovation.
Which is negative since it is to the left of the mean. Now let's plug in the gene Y measurement for this same cell and the mean value for gene Y. And that gives us this difference, which is negative because it is below the mean. And since both differences are negative, multiplying them together gives us a positive value. Now we do the same thing for the next data point. Again, since it is to the left of the solid green line, we can see that it is less than the mean for gene X. And since it is below the solid red line, we can see that it is less than the mean for gene Y. So we plug in the values for gene X, and that gives us a negative difference. Now we plug in the values for gene Y, and that gives us another negative difference. Again, since both differences are negative, multiplying them together gives us a positive value. So we see that when the values for gene X and gene Y are both less than their respective averages, we end up with positive values. Bam! The remaining three cells are to the right of the solid green line, so we see that they are all greater than the average value for gene X. And they are all above the solid red line, so we see that they are also greater than the average value for gene Y. Thus, when we plug in the values and do the math, we end up with positive values. Doing the math, I'm doing the math. Hip hip hooray, I'm doing the math. Hip hip hooray, hip hip hooray. So we see that when both values are greater than their respective means, we end up with positive numbers. In summary, data in these two quadrants contribute positive values to the total covariance. Bam! Hooray! We've calculated these terms for each cell. The sigma tells us to add up each term. And then we divide by the number of measurements, n, which in this case is 5, minus 1. And ultimately, we end up with a covariance equal to 116. Since the covariance value, 116, is positive, it means that the slope of the relationship between gene X and gene Y is positive. In other words, when the covariance value is positive, we classify the trend as positive. Double bam! Note, the covariance value itself isn't very easy to interpret and depends on the context. For example, the covariance value does not tell us if the slope of the line representing the relationship is steep or not steep. It just tells us that the slope is positive. More importantly, the covariance value doesn't tell us if the points are relatively close to the dotted line or relatively far from the dotted line. Again, it just tells us that the slope of the relationship is positive. Note, we'll talk about why the covariance value is so hard to interpret later. And remember, even though covariance is hard to interpret, it is a computational stepping stone to more interesting things. Bam! Now let's imagine we got different values for gene Y. Just like before, we can graph the data using pairs of x and y axis values.
Did you know you can make animated explainer ads in videos just like this one? It's $468.
The mean value for gene X is the same as before, 17.6. And the mean value for gene Y is 20.2. Now let's focus on the data point on the far left. Since the measurement for gene X is to the left of the solid green line, we can see that it is less than the mean value. However, the measurement for gene Y is above the solid red line, so we see that it is greater than the mean value. Thus, when we plug in the numbers and do the math, we end up with a negative number. And the same thing happens to the next data point. We end up with a negative number. So, if one value is less than its mean and one value is more than its mean, we end up with a negative number. Bam! Likewise, these cells also result in negative numbers because they are greater than gene X's mean and less than gene Y's mean. In summary, data in these quadrants contribute negative values to the covariance. Now we add up each term, and then we divide by the number of measurements n, which is 5 minus 1. And ultimately, we end up with a covariance equal to negative 105.15. Since the covariance value, negative 105.15, is negative, it means that the slope of the relationship between gene X and gene Y is negative. Again, covariance doesn't tell us if the slope is steep or not. And, more importantly, covariance doesn't tell us if the points are relatively close to the line or relatively far. Just that the slope is negative. Bam! Now let's calculate the covariance for when there is no trend. In this case, every value for gene X corresponds to the same value for gene Y. First, we calculate the means. Then we do the math for the first point. The difference from gene X's average is negative 14.6. And the difference from gene Y's average is 0. And anything times 0 is 0. So the value for the first data point is 0. Likewise, because the differences between the gene Y values and the gene Y average are all 0, all of the remaining terms are 0. Doing the rest of the math gives us 0 in the numerator, and the whole thing equals 0. Likewise, when every value for gene Y corresponds to the same value for gene X, the covariance equals 0. In this last case, we can see that, even though there are multiple values for gene X and Y, there is still no trend because as gene X increases, gene Y increases and decreases. In other words, the negative value for this point is canceled out by this positive point. And this positive point is canceled out by this negative point, and the covariance equals 0. So we see that the covariance equals 0 when there is no relationship between gene X and gene Y. Double bam! Now let's talk about why the covariance value is hard to interpret. To see why the covariance value is difficult to interpret, let's go all the way back to looking at just gene X and calculate the covariance between gene X and itself. Just like before, we can plot the data. And the mean value for gene X is the same as before, 17.6. And we use 17.6 on the y-axis as well. Now we are ready to calculate the covariance. Note, in this case, the same data are on both axes, and that means x equals y and x bar equals y bar. So we can replace y with x and y bar with x bar. And then we can multiply x minus x bar times x minus x bar. And we are left with the formula for estimating variance. In other words, the covariance for gene X with itself is the same thing as the estimated variance for gene X. Now, when we do the math, we get 102. Since the covariance value is positive, we know that the relationship between gene X and itself has a positive slope. So let's move the graph and the covariance value over here and see what happens when we multiply the data by 2. Now, the x and y axis labels on the right are twice what they are on the left. And the new mean values are twice what they were before. But the relative positions of the data did not change. And each dot still falls on the same straight line with positive slope. In other words, the only thing that changed was the scale that the data is on. However, when we do the math, we get covariance equals 408, which is 4 times what we got before. Thus, we see that the covariance value changes even when the relationship does not. In other words, covariance values are sensitive to the scale of the data, and this makes them difficult to interpret. This sensitivity to scale also prevents the covariance value from telling us if the data are close to the dotted line that represents the relationship or far from it. In this example, the covariance on the left, when each point is on the dotted line, is 102. And the covariance on the right, when the data are relatively far from the dotted line, is 381. So, in this case, when the data are far from the line, the covariance is larger. Now let's just change the scale on the right-hand side and recalculate the covariance. And now the covariance is less for the data that does not fall on the line. If you're thinking, I sure wish there was something to describe relationships that wasn't sensitive to the scale of the data, then you're in luck. Calculating covariance is the first step in calculating correlation. Correlation describes relationships and is not sensitive to the scale of the data. And we'll talk about correlation more in the next video in this series. It's also worth mentioning that covariance values are used as stepping stones in a wide variety of analyses. For example, covariance values were used for principal component analysis, PCA, and are still used in other settings as computational stepping stones to other, more interesting things. Bam! In summary, covariance is a way to classify 3 types of relationships. 1. When the covariance is positive, it means the relationship has a positive slope. 2. When the covariance is negative, it means the relationship has a negative slope. and 3. When covariance equals 0, there is no relationship because there is no trend. The covariance value itself is difficult to interpret. However, it is useful for calculating correlations and in other computational settings. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more,
Oke, kita lanjut. Oke, ini harusnya yang tadi ya, ini objektif pembelajaran untuk yang tadi pembelajaran hari ini itu sama. Kayaknya ini kedouble tadi. Oke, tadi ada min ya. Jadi di mana di sini itu D itu data, E itu expected value-nya. Kita udah sempat dengar juga ya buat perhitungan min. Oke. Dijumlahin dulu lalu dibagi banyaknya untuk dapat average-nya min. Oke, tadi juga ada variance sama D itu datanya, lalu E itu expected-nya, expected value-nya. Oke, ini yang tadi sama dijumlahin dulu baru dibagi jumlah datanya. Terus juga udah ada tadi covariance. Mungkin aku mau tanya sih. Kan tadi kita udah dengerin nih tentang variance dan covariance. Kira-kira ada yang tahu nggak nih bedanya varian dan covarian itu apa? Ada yang tahu nggak nih? Nggak usah bedanya deh. Covarian, yang pertama dulu tuh covarian dan varian itu apa? Kalau varian itu apa, covarian itu apa gitu. Karena kayaknya di slide itu nggak dijelasin tentang varian dan covarian. Oke. Kalau di dalam statistik ya, varian itu tuh kayak penyebaran kumpulan data di sekitar nilai rata-rata atau min tadi ya. Sedangkan kalau si covarian itu dia tuh ukuran hubungan antara dua variabel acak gitu. Kan tadi juga udah sempat kita tonton ya yang tentang covarian. Di covarian itu kan tadi dapat mengukur pergerakan dari dua variabel. Nah, tapi tidak dapat menunjukkan sejauh mana kedua variabel itu tuh kayak bergerak dalam kaitan satu sama lain gitu. Biasanya kalau varian itu sering dipakai juga kayak di ini ya, buat saham gitu untuk mengukur volatilitasnya. Terus kalau yang covarian biasa buat kayak ini ya, untuk yang di portofolio investor gitu kayak mendiversifikasi. Nah, itu juga bisa terus kayak cari ini portofolio yang investor gitu, itu pakai covarian. Jadi yang kelihatan aset naik turun untuk pengembaliannya seperti itu tuh pakai covarian gitu ya. Tuh. Oke, kita lanjut sebentar ini. Oke, bahasanya Inggris. Oke.
In the last video, we talked about different ways to represent the central tendency or the average of a data set. What we're going to do in this video is to expand that a little bit to understand how spread apart the data is as well. So let's just think about this a little bit. Let's say I have negative 10, 0, 10, 20, and 30. Let's say that's one data set right there. And let's say the other data set is 8, 9, 10, 11, and 12. Now, in both, let's calculate the arithmetic mean for both of these data sets. So let's calculate the mean. And when you go further on in statistics, you're going to understand the difference between a population and a sample. We're assuming that this is the entire population of our data. This is the entire population of our data. So we're going to be dealing with the population mean. We're going to be dealing with, as you see, the population measures of dispersion. I know these are all fancy words. In the future, you're not going to have all of the data. You're just going to have some samples of it, and you're going to try to estimate things for the entire population. So I don't want you to worry too much about that just now, but if you are going to go further in statistics, I just want to make that clarification. Now, the population mean, or the arithmetic mean of this data set right here, it is negative 10 plus 0 plus 10 plus 20 plus 30 over, we have 5 data points over 5. And what is this equal to? That negative 10 cancels out with that 10. 20 plus 30 is 50 divided by 5. It's equal to 10. Now, what's the mean of this data set? 8 plus 9 plus 10 plus 11 plus 12. All of that over 5. And the way we could think about it, 8 plus 12 is 20. 9 plus 11 is another 20, so that's 40. And then we have a 50 there. Add another 10. So this is, once again, is going to be 50 over 5. So this has the exact same sample. Well, no, let me be very close. They have the exact same population means. Or if you don't want to worry about the word population or sample and all of that, they have both of these data sets have the exact same arithmetic mean. When you average all these numbers and divide by 5, or when you take the sum of these numbers, divide by 5, you get 10. Some of these numbers divided by 5, you get 10 as well. But clearly, these sets of numbers are different. You know, if you just looked at this number, you say, oh, maybe these sets are very similar to each other. But when you look at these two data sets, one thing might pop out at you. All of these numbers are very close to 10. I mean, the furthest number here is 2 away from 10. 12 is only 2 away from 10. Here, these numbers are further away from 10. Even the closer ones are still 10 away, and then these guys are 20 away from 10. So this right here, this data set right here is more disperse. More disperse, right? These guys are further away from our mean than these guys are from this mean. So let's think about different ways we can measure dispersion, or how far away we are from the center on average. Now, one way, this is kind of the most simple way, is the range. And you won't see it used too often, but it's kind of a very simple way of understanding how far is the spread between the largest and the smallest number. And literally, you take the largest number, which is 30 in our example, and from that you subtract the smallest number. So 30 minus negative 10, which is equal to 40, which tells us that the difference between the largest and the smallest number is 40. So we have a range of 40 for this data set. Here, the range is the largest number, 12, minus the smallest number, which is 8, which is equal to 4. So here, range is actually a pretty good measure of dispersion. We say, okay, both of these guys have a mean of 10. But when I look at the range, this guy has a much larger range. So that tells me this is a more dispersed set. But range is always not going to tell you the whole picture. You might have two data sets with the exact same range, where still, based on how things are bunched up,
it could still have very different distributions of where the numbers lie. Now, the one that you'll see used most often is called the variance. The variance. Actually, you're going to see the standard deviation in this video. That's probably what's used most often, but it has a very close relationship to the variance. So the symbol for the variance, and we're going to deal with the population variance. Once again, we're assuming that this is all of the data for our whole population, that we're not just sampling, taking a subset of the data. So the variance, its symbol is literally this sigma, this Greek letter squared. That is the symbol for variance. And we'll see that the sigma letter actually is the symbol for standard deviation. And that is for a reason. But anyway, the definition of variance is you literally take each of these data points, find the difference between those data points and your mean, square them, and then take the average of those squares. I know that sounds very complicated, but when I actually calculate it, you're going to see it's not too bad. So remember, the mean here is 10. So I take the first data point. I say let me do it over here. Let me scroll down a little bit. So I take the first data point, negative 10. From that, I'm going to subtract our mean, and I'm going to square that. So I just found the difference from that first data point to the mean and squared it. And that's essentially to make it positive. Plus the second data point, 0 minus 10 minus the mean. This is the mean. This is that 10 right there, squared. Plus 10 minus 10 squared. That's the middle 10 right there. Plus 20 minus 10. That's a 20 squared. Plus 30 minus 10 squared. So this is the squared differences between each number and the mean. This is the mean. This is the mean right there. That is the mean. I'm finding the difference between every data point and the mean, squaring them, summing them up, and then dividing by that number of data points. I'm taking the average of these numbers, of the squared distances. So when you say it kind of verbally, it sounds very complicated, but you're just taking each number, how far, what's the difference between that, the mean, square it, take the average of those. So I have 1, 2, 3, 4, 5, divide by 5. So what is this going to be equal to? What is this going to be equal to? Negative 10 minus 10 is negative 20. Negative 20 squared is 400. 0 minus 10 is negative 10 squared is 100, so plus 100. 10 minus 10 squared, that's just 0 squared, which is 0. Plus 20 minus 10 is 10 squared is 100. Plus 30 minus 10, which is 20 squared, is 400. All of that over 5. And what do we have here? 400 plus 100 is 500, plus another 500 is 1,000. It's equal to 1,000 over 5, which is equal to 200. So in this situation, our variance is going to be 200. That's our measure of dispersion there. And let's compare it to this data set over here. Let's compare it to the variance of this less dispersed data set. So let me scroll over a little bit. So we have some real estate, although I'm running out. Maybe I could scroll up here. There you go. So let me calculate the variance of this data set. So we already know its mean. So its variance of this data set is going to be equal to 8 minus 10 squared plus 9 minus 10 squared plus 10 minus 10 squared plus 11 minus 10. Let me scroll up a little bit. Squared plus 12 minus 10 squared. Remember that 10 is just the mean that we calculated. You have to calculate the mean first. Divided by, we have 1, 2, 3, 4, 5 squared differences. So this is going to be equal to 8 minus 10 is negative 2 squared is positive 4. 9 minus 10 is negative 1 squared is positive 1. 10 minus 10 is 0 squared. You still get 0. 11 minus 10 is 1 squared. You get 1. 12 minus 10 is 2 squared. You get 4. And what is this equal to? All of that over 5. This is 10 over 5. So this is going to be, all right, this is 10 over 5. 10 over 5, which is equal to 2. So the variance here, let me make sure I got that right. Yes, we have 10 over 5. So the variance of this less dispersed data set is a lot smaller. The variance here, the variance of this data set right here is only 2. So that gave you a sense. That tells you, look, this is definitely a less dispersed data set than that there. Now, the problem with the variance is you're taking these numbers, you're taking the difference between them and the mean, then you're squaring it. It kind of gives you a bit of an arbitrary number. And if you're dealing with units, let's say if these are each, negative, well, let's say these are, let's say they're distances. So this is negative 10 meters, 0 meters, 10 meters, this is 8 meters, so on and so forth. Then when you square it, you get your variance in terms of meters squared. It's kind of an odd set of units. So what people like to do is talk in terms of standard deviation. Standard deviation. Standard deviation, which is just the square root of the variance. It's just the square root of the variance, or the square root of sigma squared. And the symbol for the standard deviation is just sigma. So now that we figured out the variance, very easy to figure out the standard deviation of both of these characters. The standard deviation of this first one up here, of this first data set, is going to be the square root of 200. Square root of 200 is what? The square root of 2 times 100. This is equal to 10 square roots of 2. That's that first data set. Now, the variance of the second data set is just going to be the square root of 2. Variance is going to be the square root of that. Sorry, the standard deviation of the second data set is just going to be the square root of its variance, which is 2, which is just 2. So the second data set has 1/10 the standard deviation as this first data set. This is 10 roots of 2. This is just the root of 2. So this is 10 times the standard deviation. 10 times the standard deviation. And this hopefully will make a little bit more sense. Let's think about it. This has 10 times more the standard deviation than this. And let's remember how we calculated. Variance, we just took the each data point, how far is away from the mean, squared that, took the average of those. Then we took the square root, really just to make the units look nice. But the end result is we said that that first data set has 10 times the standard deviation as the second data set. So let's look at the two data sets. This has 10 times the standard deviation. 10 times the standard deviation. Standard deviation. Which makes sense intuitively, right? I mean, they both have a 10 in here, but each of these guys, 9 is only 1 away from the 10. 0 is 10 away from the 10, 10 less. 8 is only 2 away. This guy's 20 away. So it's 10 times on average further away. So the standard deviation, at least in my sense, is giving a much better sense of how far away on average we are from the mean. Anyway, hopefully you found that useful.
So,
Oke, kita lanjut. Oke, di sini ada spread, the 5 main value of measuring spread itu ada range, bottom to top, atau quartile. Yang kedua itu dibagi 4. Terus juga ada interquartile range atau EQR, itu Q1 sampai Q3. Juga ada variance dan standard deviation atau simpangan baku. Oke, di sini spread ada standard deviation dibagi atau variance. Dibagi variance. Itu average distance of all measure value from the mean value. Terus juga ada range tadi, distance between lowest and highest value of a distribution. Terus juga ada quantile distance. The spectrum in which the middle 50% of the value lie. Difference between the first and the third quartile. Okay. Di Jadi ini tadi ya, kalau di sini kayak ada gambarnya, ada yang merah, ada yang biru gitu ya. Oke, ini ada garisnya. Kalau yang ini itu berarti average measure value-nya from the mean value. Terus distance between the lowest and the highest. Jadi yang dari yang paling pendek sampai yang paling tinggi itu distance yang dihitung. Terus yang ini spectrum in which the middle 50% lie. Jadi yang dihitung yang dari sini sampai sini ya. Oke. Oke, di sini ada rumus variance dan standard deviation. Ya, rumus variance dalam populasi. Oke, variance sigma n I sama dengan 1 xj kurangi Oke, bagi pangkat 2 per n perbanyaknya. Untuk standard deviation itu sama kayak yang di atas, tapi ini akar dari varian gitu. Terus untuk varian sampel sigma n I sama dengan 1 xi dikurangi x pangkat 2 per n min 1. Terus untuk standard deviation-nya juga sama, tinggal ditambah akar dari varian sampel. Oke, kita lanjut ke linear transformation.
You now know what a transformation is, so let's introduce a more a special kind of transformation called a linear transformation. It only makes sense that we have something called a linear transformation because we're studying linear algebra. We already had linear combinations, so we might as well have a linear transformation. And a linear transformation, by definition, is a transformation, which we know is just a function. We could say it's from the set Rm, or let me say it from Rn to Rm, and it might be obvious in the next video why I'm being a little bit particular about that, although they are just arbitrary letters, where the following two things have to be true. So if something is a linear transformation, if and only if the following thing is true. Let's say that we have two vectors, say vector A and let's say vector B, are both members of Rn. So they're both in our domain. So then this is a linear transformation if and only if I take the transformation of the sum of our two vectors, if I add them up first, that's equivalent to taking the transformation of each of the vectors, and then summing them. So that's my first condition for this to be a linear transformation. And then the second one is that if I take the transformation of any scaled up version of a vector, so let me just multiply vector A times some scalar, some real number c. If this is a linear transformation, then this should be equal to c times the transformation of A. That seems pretty straightforward. Let's see if we can apply these rules to figure out if some actual transformations are linear or not. So let me define a transformation. Let's say that I have the transformation T. Part of my definition, I'm going to tell you it maps from R2 to, let's do something, well, let's just say it maps from R2 to R2. And it maps, so if you give it a 2 tuple, right? Its domain is 2 tuple. So you give it an x1 and an x2. Let's say it maps to. So this will be equal to, or it's associated with. It's associated with. Let me just say, let's say x1 plus x2. And then let's just say it's 3 times x1 is the second tuple. And we could have written this more in vector form. This is kind of our tuple form. We could have written it, and it's good to see all the different notations that you might encounter. You could write it that a transformation of some vector x, where the vector looks like this, x1, x2. Let me put a bracket there. It equals some new vector, x1 plus x2. And then the second component of the new vector would be 3x1. That's a completely legitimate way to express our transformation. And the third way, which I never see, but to me it kind of captures the essence of what a transformation is. It's just a mapping, or it's just a function. We could say that the transformation is a mapping from any vector in R2 that looks like this, x1, x2, to, and I'll do this notation, to a vector that looks like this, x1 plus x2, and then 3x1. All of these statements are equivalent. But our whole point of writing this is to figure out whether t is linearly independent. So I want to, sorry, not linearly independent, whether it's a linear transformation. I was so obsessed with linear independence for so many videos, it's hard to get it out of my brain in this one. Whether it's a linear transformation. So let's test our two conditions. I have them up here. So let's take t of, let's say I have two vectors a and b. They're members of R2. So let me write it. A is equal to a1, a2. And b is equal to b1, b2. Sorry, that's not a vector. I have to make sure that those are scalars. These are the components of a vector. And b2. So what is a1 plus b? What is vector a plus vector b? Brain's malfunctioning. All right. Well, you just add up their components. This is the definition of vector addition. So it's a1 plus b1. Add up the first components. And the second components is just the sum of each of the vector second components, a2 plus b2. Nothing new here. But what is the transformation of this vector? So the transformation of vector a plus vector b, we could write it like this. That would be the same thing as the transformation of this vector, which is just a1 plus b1 and a2 plus b2, which we know it equals a vector. It equals this vector, where what we do is for the first component here, we add up the two components on this side. So the first component here is going to be these two guys added up. So it's a1 plus a2 plus b1 plus b2. And then the second component, by our transformation or our function definition, is just 3 times the first component in our domain, I guess we could say it. So it's 3 times the first one. So it's going to be 3 times this first guy. So it's 3a1 plus 3b1. Fair enough. Now, what is the transformation individually of a and b? So the transformation of a is equal to the transformation of a. Let me write it this way. It's equal to the transformation of a1, a2 in brackets. That's another way of writing vector a. And what is that equal to? That's our definition of our transformation right up here. So this is going to be equal to the vector a1 plus a2, and then 3 times a1. Just comes straight out of this definition. I essentially just replaced an x with a's. By the same, I guess, argument, what is the transformation of our vector b? Well, it's just going to be the same thing with the a's replaced by the b. So the transformation of our vector b is going to be, b is just b1, b2, b1, b2. So it's going to be b1 plus b2. And then the second component in the transformation will be 3 times b1. Now, what is the transformation of vector a plus the transformation of vector b? What's this vector plus that vector? And what is that equal to? Well, this is just pure vector addition. So we just add up their components. So it's a1 plus a2 plus b1 plus b2. That's just that component plus that component. The second component is 3a1. We're going to add it to that second component. So it's 3a1 plus 3b1. Now, we just showed you that if I take the transformation separately of each of the vectors and then add them up, I get the exact same thing as if I took the vectors and added them up first and then took the transformation. So we've met our first criteria, that the transformation of the sum of the vectors is the same thing as the sum of the transformations. Now let's see if this works with a random scalar. So we know what the transformation of A looks like. What is a transformation? Well, what does CA look like, first of all? I guess that's a good place to start. C times our vector A is going to be equal to C times A1 and then C times A2. That's our definition of scalar multiplication times a vector. So what's our transformation? Let me go to a new color. What is our, let me do a color I haven't used in a long time, white. What is our transformation of CA going to be? Well, that's the same thing as our transformation of CA1, CA2, which is equal to a new vector where the first term, let's go to our definition, is you sum the first and second components, and then the second term is 3 times the first component. So our first term, you sum them, so it's going to be CA1 plus CA2. And then our second term is 3 times our first term, so it's 3CA1. Now, what is this equal to? This is the same thing. You can view it as factoring out the C. This is the same thing as C times the vector A1 plus A2. And then the second component is 3a1. But this thing right here, we already saw. This is the same thing as the transformation of A. Transformation of A. So just like that, you see that the transformation of C times our vector A, for any vector A in R2, anything in R2 can be represented this way, it's the same thing as C times the transformation of A. So we've met our second condition. That it doesn't, that well, I just stated it, so I don't have to restate it. So we meet both conditions. We meet both conditions, which tells us that this is a linear transformation. And you might be thinking, OK, Sal, fair enough. That was, how do I know that all transformations aren't linear transformations? Show me something that won't work. And here I'll do a very simple example. Let me define my transformation. And just to make it, let me do one. Let me make it. Let me define a transformation. Well, I'll do it from R2 to R2 just to kind of compare the two. I could have done it from R to R if I wanted a simpler example. But I'm going to define my transformation. Let's say my transformation of the vector x1, x2. Let's say it is equal to, let me just say x1 squared and then 0. Just like that. Let me see if this is a linear transformation. So the first question is, let's take, what's my transformation of a vector A? So my transformation of a vector A, where A is just the same A that I did before, it would look like this. It would look like a1 squared and then a 0. Now, what would be my transformation? What would be my transformation if I took C times A? C times A. Well, this is the same thing as C times A1 and C times A2. And by our transformation definition, if I take, the transformation of C times of this thing right here, because I'm taking the transformation on both sides. And by our transformation definition, this will just be equal to a new vector that would be in our codomain, where the first term is just the first term of our input squared. So it's CA1 squared, CA1 squared, and the second term is 0. And what is this equal to? Let me switch colors. This is equal to C squared A1 squared, and this is equal to 0. Now, let's see if we can factor out, if we can assume that C does not equal 0, this would be equal to what? This would be, actually, it doesn't even matter. We don't even have to make that assumption. So this is the same thing. This is equal to C squared times the vector A1 squared 0, which is equal to what? this is equal, this expression right here is a transformation of a. So this is equal to c squared times the transformation of a. Let me do it in the same color. Times the transformation of a. So what I've just showed you is if I take the transformation of a vector being multiplied by a scalar quantity first, that's equal to, for this t, for this transformation that I've defined right here, that's equal to c squared times the transformation of a. And clearly, this statement right here for this choice of transformation conflicts with this requirement for a linear transformation. If I have a c here, I should see a c here. But in our case, I have a c here and I have a c squared here. So clearly, this negates that statement. So we're definitely not dealing. So this is not a linear transformation. And just to get a gut feel, if you're just looking at something, whether it's going to be a linear transformation or not, if the transformation just involves linear combinations of the different components of the inputs, you're probably dealing with a linear transformation. If you start seeing things where the components start getting multiplied by each other, or you start seeing squares or exponents, you're probably not dealing with a linear transformation. And then there are some functions that might be in a bit of a gray area. But it tends to be just linear combinations are going to lead to a linear transformation. But hopefully that gives you a good sense of things. And this leads up to what I think is one of the neatest outcomes in the next video.
Oke, tadi dijelasin untuk yang linear transformation. Oke. Jadi ini linear transformation of data set. Jadi D itu data, kayak yang tadi. Jadi datanya ada -1, 2, 3 gitu. Terus yang tadi E itu yang expected value. D sama dengan -1 tambah 2 tambah 3 per 3 sama dengan 4 per 3. Jadi D aksen itu 1, ini plus 4, terus 5. Jadi D-nya 2. Ini dipindah ke sini, yang 2-nya tadi pindah ke sini. Jadi 1 tambah 4 tambah 5 per 3, 10 per 3, karena 4 per 3 tambah 2. Terus expected value D ditambah A tambah ED. Tadi kita udah dapat ED aksen sama ED. Terus 2 aksen itu -4, -2, 4, 6. Kita juga hitung expected value dari data 2 aksen ini dimasukin, dibagi banyaknya 3, sama dengan 8 per 3. Kita masukin tadi yang ED. Terus ini ada scaling factornya 2. Terus berarti D yang ini sama dengan, ini tadi lambang untuk yang ini ya. Terus linear transformation-nya var D sama dengan var D plus A. Ini kayaknya lambang theta ya. Ini nggak ada penjelasan lambangnya, tapi nanti bisa ditonton ya, karena di akhir slide ini tuh ada playlist buat video dari potongan-potongan gambar ini. Itu bisa ditonton sendiri nanti. Tuh. Alpha ya. Terus kita Lanjut ke demonya aja ya. Demo mean covariance effect on linear transformation. Di week ini kita akan investigate how the mean and covariance of dataset change when we apply a fine transformation to the dataset. Import package-nya dulu. Oke, di sini kita import package-nya terlebih dahulu. Terus next, you're going to retrieve Olivetti Fish dataset. Kita pakai Olivetti Fish dataset. Ketika kita menjalankan beberapa dataset sebelum digging into further analysis, it is almost always useful to do a few things to understand your dataset. First of all, answer the following set question. Jadi kita harus tahu size dari dataset kita terlebih dahulu, sama kita harus tahu dimensionality dari data kita. Sini the dataset we have are usually stored as dua dimensi matrix. Then it would be really important to know which dimension represent the dimension of the dataset and which represent the data point in the dataset. Okay, when you implement the function for your assignment, make sure you read the docstring for what each dimension of your input represent the data point and which represent the dimension of the dataset. Oke, di sini kita bikin shape image-nya 64,64, kita load fetch dataset-nya. Tadi fetch Olivetti, fetch dataset home. Ini untuk path-nya. Fetch sama dengan dataset.data. Kita print shape of the dataset. Di sini shape-nya 400,4096. Ada 400 data point. When your dataset are image, it's really good idea to see what they look like. One very convenient tool in Jupyter is interact with widget. Di sini which we use to visualize the image atau gambar yang tadi yang fetch. For more information how to use interact, have look at the documentation. Ini untuk penggunaan interact-nya ya. Nanti bisa sambil dilihat-lihat lagi untuk penggunaan interact ini. Terus kita import dulu widget, import interact. Terus kita bikin fungsi def show face. Terus dia bakalan nampilin face-nya reshape 64,64, color-nya gray. Oke. Interact and dengan 0 dan face min 1. Def display face. Ini ada fungsi untuk men-display face-nya. Kalau kita naikin ini ya. Ini 13, 6, 3. Oke, kita bisa lihat ya data-datanya ya. Nih. Nih, ada penjelasannya. The purpose of the following block is to compute the mean and covariance of dataset of size, where n is the number of data point and d is the dimensional of each data point. Oke, kita running yang mean and covariance of dataset. Kita bikin fungsi mean naive. Dia terima variabel x, compute the mean for a dataset by iterating over the dataset argument. Jadi tadi ini x, n, d itu tadi dijelasin dataset size. And the array representing the dataset, dia akan nge-return si mean and the array which is the mean of the dataset. And d sama dengan x shape. Oke, nanti dia akan nge-return mean-nya. Terus di sini ada lagi fungsi covnaive. Jadi mean sekarang covariant. Jadi ini compute the covariant for dataset argument. Jadi argumennya dia terimanya ini inputnya x sama kayak sebenarnya x, tapi dia di sini nge-return covariannya. Di sini ada fungsi sama ya tadi kayak yang tadi min sama cov. Kalau tadi ada naive-nya, min naive, cov naive, di sini min sama cov aja. Min untuk compute the mean for dataset, argumennya ada x, and the array representing the dataset, terus dia akan nge-return min-nya. Di sini juga ada yang covariant, compute the covariant for the dataset. Dia terima inputnya sama x, dia akan nge-return covariance matrix, and the array which is the covariant matrix of the dataset. Ada lagi min buat phase, def min buat phase-nya, di compute the mean of the phase argument and 64 kali 64. Dia akan nge-show image-nya. Oke, ini ya hasilnya. Ya, di sini we have some huge data matrix and we want to compute its mean. X sama dengan NP random dan 100.000,20 benchmarking time for computing mean. Percent time, mean naive, kita panggil mean naive sama panggil yang mean tadi. CPU time, kita bisa lihat di sini time-nya user 116 second ms, sistem 0 ms, total 116 ms. Terus wall time. Yang atas untuk yang min, naive, yang bawah untuk yang min. Terus juga kita bisa lihat benchmarking time untuk compute covariance-nya. Yang atas untuk cov naive, yang bawah untuk cov. Kita bikin fungsi time, a helper function to time the execution of a function. F, dia terima argumen F, itu function which we want to take time it. Terus habis itu repeat to the number of the time we want to execute F. Terus dia akan nge-return mean dan standard deviation. Oke, dia bikin times try kosong, dia masukin di for loop. Terus dia akan nge-return mean sama STD, standard deviation. Sini bikin fast time sama slow time. Bikin looping for size in NP range 100,500 step sama dengan 100. Oke. Di sini slow time sama dengan NP array fast time sama dengan NP array fast time, slow time sama dengan NP array slow time. Oke, kita visualisasiin. Di sini ini running time-nya. Yang biru itu yang fast min, yang orange yang naive min. Di sini size of dataset-nya. Terus kita lanjut bagian yang kedua, affine transformation of dataset. In this week, we are also going to verify a few properties about the mean and covariance to affine transformation of random variables. Consider a data matrix X of size n, D. Jadi ini shape-nya ya, n, D. We would like to know what is the covariance when we apply affine transformation AXE plus B for each data point XE in X. We would like to know what happened to the mean and covariance for the new dataset if we apply affine transformation. Oke, di sini ada affine mean. Di sini untuk compute the mean after affine transformation. Dia terima argumen mean A, B ya tadi. A, B itu affine transformation applied to X. X-nya itu and the array to the mean vector. Mean-nya berarti dia. Kita affine M. Affine M sama dengan np0 main.shape. Update affine M-nya A admin plus B return affine M. Kita bikin yang covariance. Compute the covariance metric after affine transformation. Dia terima SAB. S itu and the array and the covariance metric. A, B itu affine transformation applied to each element in X. They return covariance matrix after the transformation. Okay. And next, ini kita masukin from numpy.testing, import, assert, close. Masukin A, NP array-nya 0,1, 2,3, B, 2, M, NP full 2,2, S, NP A 2, pangkat 2 kali 2. Expected affine mean, NP array, expected affine cov. Oke, ini from numpy testing. Jadi untuk yang min ada, ini nggak ada yang min cov langsung, terus kita assert all close. Okay, next we can generate some random data set. X adalah random. Ini untuk yang random data setnya. Assuming that for some data set X, the mean and covariance are M, S, and for the new data set after affine transformation x-accent, the mean and covariance are m-accent and s-accent. Then we will have to the following identity. Ya, m-accent sama dengan affine mean, m, a, b, s-accent sama dengan affine covariance, s, a, b. Kita buat yang ini yang X untuk apply si affine transformation. Yang pertama, ini yang kedua. One very useful way to compare whether arrays are equal or similar is use the helper function in numpy.testing. Ini bisa kita lihat juga nanti dokumentasinya. Ini dokumentasinya yang numpy.testing. Jadi kita pakai yang assert yang all close. Oke, NP testing assert all close mean X1. Oke. Ini untuk mean covariance of a dataset effect on linear transformation. Oke. Inner product kita tinggal dulu untuk hari Rabu besok. Kita coba lihat yang NumPy dulu. Oke, di sini introduction to NumPy. NumPy is a fundamental package for scientific computing in Python. It is a Python library that provides a multidimensional array object. In this course, we will using NumPy for linear algebra. If you're interested in learning more about NumPy, you can find, kita bisa lihat dokumentasinya. Oke, kita panggil sini, kita import NumPy SNP. We commonly use the NP over. Oke, kita emang sering pakainya NP untuk nge-referring si NumPy. Kita create NumPy array. Ini contoh kalau untuk yang NumPy ini udah sering ya kita pakai. Oke, ini untuk dua multidimensional NumPy array. Sini NP shape. Untuk dapat shape dari NumPy array-nya di sini. Sini ada note the difference in shape between one-dimensional and two-dimensional array. For two-dimensional array, you can consider the first element of the tuple to be the number of row and the second element to be the number of column. Sudah lanjut creating NumPy array based on shape. Oke, ini tadi kita juga udah pakai ya waktu kita jalanin yang mean covariant itu kita juga pakai NP0 sama NP1. The input of the function is the shape of NumPy array which you want to get. Ini kita coba NP.0 5. Berarti ini ada 5 gitu ya. Print A. Virus 2,3 berarti ada, jadi yang belakang itu buat kolom. Ya, second itu kolom, yang pertama tuh row-nya. Ini sebanyak itu berarti akan 0 gitu. Kalau once itu akan diisi 1. Terus reshaping array. Di sini kita pakai np reshape to change the shape of numpy array. One use of this function is to change one-dimensional numpy array to two-dimensional row vector or column vector. Okay, di sini you pass in the required dimension which the array needs to be reshaped to as input to the function. One of the value in the tuple can be 1, can be min 1, negative 1. This value shall then be determined automatically. Sini kalau kita juga reshape bisa pakai use in conjunction with np range tadi. Kalau yang di sini kita pakai yang range. Ini tadi yang np zeros juga udah atas tadi. A sama dengan np range 3 0 1 2 print A. Terus shape-nya A 3, kalau kita reshape yang 1, min 1, oke, hasilnya kayak gini ya. Karena the first value of the tuple is 1 because the row vector only has one row. Shape-nya 1,3. Sini kita pakai reshape min 1,1. Jadi minnya yang di belakang, sekarang minnya yang di depan. Hasilnya kayak gini. Terus di sini reshaping an array we get from arrange. Kita pakai yang arrange. Sama dengan np arrange. Oke, ini 0 sampai 5 karena kita np arrange 6 jadi sebanyak 6. Ini 1,5 kita lihat A-nya 6, print A shape. Terus kita pakai yang kedua A sama dengan A reshape 3,2. Kalau 3,2 kayak gini. Oke, ini print A-nya, terus shape-nya. Oke, kita coba bandingin langsung sama si arrange. Oke, NP. Oke, kenapa yang ini nggak bisa kayak gini? Kalau tadi kan kita masukin nih NP arrange. Kalau kita masukinnya, kita mau bandingin sama yang bawah. Ini kan tadi reshape, sedangkan bisa pakai arrange sama reshape gitu ya. Kenapa kalau yang bawah nggak bisa? Kita ganti arrange. Oke, bisa ya. Karena tadi cuma kedouble. Ngomongnya. Tapi dia nggak ngehasilin apa-apa kalau kita arrange gitu. Ada yang tahu nggak kenapa kan dia ngehasilnya kosong gini. Oke, ini ya tadi NP arrange. Nih, kalau kita mau ada isinya, kita harus nyebutin type-nya nih. Sedangkan tadi aku tulis tanpa type-nya. Ini arrange kalau cuma satu. Tapi kalau kita arrange 3,7 ini harusnya bisa ya. Coba. Oke, ini ya. 2,5 NP arrange 2,5 hasilnya 2, 3, 4. NP arrange 3,7 hasilnya 3, 4, 5, 6. Oke, kita next. Accessing NumPy array. Oke, nah, kita bikin depth trace untuk find the trace of A. Sini argumennya A itu, oke, kalau angka depannya lebih besar, jadi nggak bisa ya? Iya, kalau angka depannya lebih besar itu nggak bisa. Nih ya, tadi kalau misal 5,2, hasilnya kosong. Tapi kalau kita misal 2,9, berarti nanti yang tampil itu dari angka 2 sampai 8. Nah, nih. Jadi nggak boleh yang depan lebih besar. Sampai array bisa diisi huruf enggak. Ini sampai array. Nah, kita lihat ya kalau yang arrange. Oke. Generate pattern with integer that have a arbitrary size. Harus nggak bisa huruf deh kayaknya ini. Ini nggak bisa huruf. Iya, bisa. Bisa di-convert. Kalau ini untuk yang numpy.arrange. Jadi kalau yang tadi kita pakai kan si numpy.arrange. Kalau yang arrange cuma bisa angka. Nggak bisa buat huruf. Oke, kita next accessing NumPy array. You can use the common square bracket notation for accessing the element of NumPy array. If A is one-dimensional array, then you can use AE to access the E element of A. Apakah bisa menampilkan seluruh data kolom, misal A, data. Oke. Kalau di sini karena kita masukinnya cuman di atas gini ya, habis itu kita masukin datanya kayak gini aja gitu ya. Terus kita bisa tampilin langsung, ini untuk yang reshape, tapi kalau untuk yang arrange, itu kita tampilin semuanya tetap kayak gini hasilnya. Ini cuman buat, ini sih reshaping array, kalau untuk di saat kita pakai di sini, sebentar, jadi ada arrange sih. Oke, ini. Yang tadi kita pakai sama kayak yang kita. Terus di sini kita masukin 105.000 step 100. Itu bisa dilihat itu step apa. Jadi lihat di sini arrange, start, stop, step. Oke, yang ini tadi. Kalau langsung ke semua, misal datanya banyak banget kayak gini tuh tetap harus pakai for sih. Oke, mungkin ada lagi. Bisa nggak misal kalau satu NumPy dari list berisi nama-nama dijadikan indeks. Ya, jadi kayak ini ada list isinya nama gitu, terus mau diubah jadi indeks. Kayak kalau di data itu kayak per nama dikasih ID gitu ya, jadian. Indeksnya itu buat gantiin si nama-namanya itu. Oke, harusnya sih bisa sih kalau masih kayak gitu, kayak yang kita olah kan tetap si indeksnya kan. Terus nanti dari indeks itu kita bisa tahu namanya yang mana. Itu sebenarnya juga bisa datanya ditambahin. Iya, bisa. Datanya bisa ditambahin si indeksnya itu deh. bisa. Kayak Manda tapi nama kolom di sisi kiri. Ya, itu boleh sih. Bisa dipanggil pakai looping. Oh iya, mumpung aku juga ingat, aku nggak untuk kelas minggu ini nggak jadi diubah ya. Jadi kelasnya tetap sama Senin, Rabu, Jumat. Jangan pada lupa buat ngumpulin proposalnya ya. Kemarin udah di-share juga di Google Classroom, juga udah di-share di Discord untuk link pengumpulannya. Batas pengumpulan untuk formnya kan kemarin ada 2 ya. Satu form proposal, yang satu itu form feedback. Itu batasnya tanggal 20 Juli ya. Untuk yang form feedback itu setiap anggota harus isi, kalau untuk form proposal itu perwakilan 1 orang aja yang isi. Di Google Stock Price ada kode gini kan, real stock price sama dengan dataset tes ilog. Itu kan itu akses kolom high, kolom kedua. Ngandet yang udah ada. Itu kalau mungkin yang maksud tampilan salah satu kolomnya ya. Iya, itu iya. Karena ini kan langsung kayak manggil dataset, satu dataset, terus dia cari lokasinya yang udah diinputin ini ya, yang 2,1,1.22 gitu ya. Jadi emang itu cuma ngambil kolom tertentu aja itu. Yang depan ya, kayak itu ngambil semua barisnya di kolom 1 sampai 2. Dari 1 ke 2. Bedanya ilog dan log. Kalau log itu, aku kayaknya jarang pakai sih yang log juga. Itu dipandas kan ya, ilog pakai indeks, log pakai label. Iya, kalau log pakai label. Kalau yang iLog pakai indeks ilog. Iya, kalau pakai log itu bisa langsung ditulis yang kayak misal datanya apa, nama datanya, terus dot log. Terus kan tadi kita mau ambil misal T2, koma, langsung aja disebutin namanya. Misal nama kolomnya itu nama gitu. Nah, langsung kayak gini kalau pakai log. Gitu. Kalau yang tadi yang pakai ilog tadi berarti karena itu indeks. Ini data ilog. Misal ini cuma satu karena nama itu ada di indeks pertama gitu. Misal contohnya kayak gitu. Keduanya dipakai untuk kolom. Ada yang row juga sih. Nggak cuma kolom. Kalau ini kan untuk kolom nih. Ini juga kolom. Kalau row itu misal kayak ini, kita mau ambil satu row aja gitu ya. Nah, kita cuma mau ambil row kedua. Sudah kita langsung R2. Itu row 2. Kalau yang log, yang ilognya itu kita langsung aja. Misal kita mau ambil satu row aja, ya udah kita langsung masukin aja gini. Kalau kayak yang ini itu kolom. Kalau yang ini row. Misal kalau row-nya banyak ya yang mau diambil gitu. Aku misal mau ambil row dari range 0 sampai 4 gitu. Ya udah dimasukin 0 sampai 4. Terus kalau yang ini tinggal dimasukin juga, ini misal dari row 1 sampai row 4. Ini kalau row, ini kalau kolom. Yang dua ini kolom, yang dua bawah itu row. So, kalau mau dapat ini indeks ke N yang nilainya tertentu dari kolom nama. Bisa kok. Itu juga bisa. Misal, kayak ya ada, misal ada, selain ada nama, di tabel yang aku punya itu ada gaji gitu ya. Jadi aku tinggal data, dot, misal kalau ini log, aku mau pakai yang log, terus aku mau dapat gajinya gitu dari semua tab, maksudnya dari isi dari semuanya. Terus aku mau ambil si gaji gitu. Terus aku mau ambil gaji dari semuanya, terus ini kalau yang pakai log itu petiknya 1 ya. Kalau pakai kalau untuk yang kayak gini yang multiple itu pakai petiknya 1. Terus aku masukin lagi, misal ini kan mau ambil dari semua ya, itu bisa kayak gini, aku mau ambil dari semua kolom, itu khusus yang gaji aja, terus misal tambahin lagi kayak yang tadi ya, untuk yang tertentu ya, ini kan cuma untuk gaji aja gitu ya. Terus kalau aku mau tambahin untuk yang tertentunya itu bisa kayak gini. Misal aku panggil dari datanya itu misal tadi data, dia punya gaji ini, dia punya gaji di data itu, terus aku kasih tambahan lagi kayak ketika gajinya yang mau ditampilin itu lebih dari 5 juta. Lebih dari sama dengan 5 juta. Nah, kayak gini. Ini beda kalau di ilok juga, ini beda nanti kalau di ilok. Kalau di ilok, karena tadi yang ilok itu indeks ya, kita harus tahu dulu lokasi gaji itu ada di kolom keberapa. Misal kolom kedua, karena nama terus gaji. Misal datanya kayak gitu. Jadi di kolom kedua gitu, di gaji. Terus kalau untuk yang di bawahnya ini, kalau tadi langsung manggil datanya di kolom apa gitu. Nah, kalau untuk yang ilok itu harus ditambahin di depannya list. Terus pakainya kurung ini. Nah, ini. Ini tinggal disesuaikan aja nanti sama yang dibutuh apa. Misal kalau mau nama tertentu ya berarti yang di sini karena nama string pakai petik gitu. Oke, mungkin ada lagi. Ini mungkin mau dihapus aja atau aku masukin juga di file ini. Jadi aku taruhin di paling bawah nanti. Terus aku komen semua biar kalau di running nggak masalah, tapi bisa buat dipakai belajar gitu. Oke. Yang lain mungkin ada lagi. Oke, kita masuk inner product di hari Rabu ya. Terus kalau tutorial NumPy ini nanti mungkin aku kasih aja ya semuanya. Jadi kalau NumPy kan emang udah pernah pada pakai ya. Di NumPy. Ini semua yang ada di NumPy gitu. Nanti bisa dilihat-lihat juga, dipelajari. Oke. Mungkin ada yang mau bertanya dulu tentang proposal atau yang lain, boleh. Untuk yang kemarin nggak ada ini ya, nggak ada kuis ya. Oke, kalau untuk Gantt itu gimana, Kak? Oke, kayaknya ada namanya tuh Microsoft Project ya, yang buat yang buat bikin Gantt chart. Untuk link GitHub itu dikumpulkan di akhir, di form yang pengumpulan akhir. Bentar, coba aku cek di form yang sekarang apakah udah ada link GitHub-nya. Harusnya sih belum ada link GitHub-nya. Ya, bukan yang ini. Oke. Ini kategori, summary project, list dataset yang digunakan, jurnal, sama file proposalnya aja. Untuk yang tadi, risk management, bentar. Oke, kalau misal ada, misal nih, dari yang misal ada dataset automatic checkout deh, enggak deh, communication. Itu kan kemarin kayak cuman bisa bikin grafnya ya, datanya. Terus butuh dataset pendukung. Nah, bisa aja risknya ini kayak datasetnya nggak bisa berkorelasi sama si graf itu. Terus dari satu kelompok itu punya rencana lain gitu dengan data itu. Terus untuk permasalahan itu kayak gimana? Ataukah akan diakalin datanya supaya bisa berkorelasi atau gimana? Kayak gitu bisa sih untuk risknya. Kalau Gantt chart itu di sini ya, kayak tanggalnya, terus yang dilakuin apa, misal problem ini ya, initiation gitu, atau ngerjain writing project gitu. Itu bisa ditulis, terus tanggalnya dari kapan sampai kapan, terus di sebelahnya itu ada kayak kotak-kotak buat isi tanggalnya, terus diwarnain gitu, kayak di highlight beda warna. Itu bisa dibikin pakai Excel juga bisa, dibikin pakai aplikasi yang untuk Gantt chart khusus juga bisa. Aku kayaknya ada sih contoh Gantt chart yang dibikin pakai Excel. Nah, kayak ini nih. Ini contoh Gantt chart yang dibikin pakai Excel. Terus ini kelihatan. Oke, yang lebih kayak gitu ya. Mungkin ada lagi. Tanya Kak, kalau pada pembagian job desk ternyata tidak semua anggota kebagian coding. Misal ada yang kebagian buat proposal, ada yang buat slide dan video, itu gimana? Apakah boleh? Boleh, boleh aja gitu. Kan yang penting mereka ada kontribusi juga di dalam pembuatannya. Kalau memang dari tim kalian sendiri nggak masalah buat anggota itu ada yang nggak menyentuh coding sama sekali, itu juga nggak masalah. Gitu. Oke. Oke, mungkin yang lain ada lagi. Untuk yang form ini yang isi satu kelompok satu orang aja ya. Ada lagi satu form yang diisi oleh semua orang. Untuk yang Kominfo Feedback 1 MLT 2. Yang ini yang barusan aku kirim, linknya itu harus diisi sama semua peserta. Yang ini ya. Nah, nanti kalau misal kayak ada yang ngerjain proposalnya atau bikin slide-nya, videonya gitu bisa ditulis di sini ya. Kontribusi secara detail gitu, mendetail. Untuk ID grupnya itu yang udah dibagi kemarin kayak yang FN1, FN2 gitu. Kalau semua berkontribusi bisa langsung disubmit. Tapi kalau ada yang nggak berkontribusi di sini atau solo, itu nanti mereka harus isi satu halaman lagi formnya. Isi satu lagi untuk ngelis nama-nama orang yang ada di kelompoknya gitu, termasuk nomor registrasinya. Oke. Mungkin kalau nggak ada yang tanya lagi, ini kita udah jam 21.59 ya. Aku izin buat stop share screen. Oke, sebentar. Oke, barusan kelempar. Tadi kayaknya ada yang tanya, kalau video tadi gimana ya? Mungkin bisa di-send ulang masalah yang tadi video. Kalau video bikin masing-masing baru digabung boleh? Boleh. Oke, boleh ya kalau misal ada yang mau juga caranya kayak gitu karena misal nggak ketemu jamnya buat di dalam satu Zoom bareng gitu, itu boleh juga digabung-gabung videonya. Oke, mungkin ada lagi yang lain. Kalau tidak, yang bisa open cam boleh open cam. Oke, cuman satu layar. Oke, aku tunggu sampai jam 22.06. Oke, ini cuma satu layar. Oke, jam 22.06. Oke, baik. Oke, kita akhiri kelas hari ini. Terima kasih buat teman-teman yang udah pada datang ke kelas hari ini. Kita ketemu lagi besok Rabu. Minggu ini kelasnya tetap sama, Senin, Rabu, Jumat. Oke, baik. Terima kasih.